So what we didn't quite finish out last time was our conversation about Laplace. We mentioned that he had written this book that was basically called The Mechanics of the Heavens, or Celestial Mécanique, I believe is what it was. This thing is 5 books long, 5 volumes, over 26 years. He wrote on this from 1799 to 1825. Okay, and we already talked about that he was trying to solve the problems of the solar system. It was approximately 2,000 pages long, and it included a lot of people's work, not just his. Let's say all relevant material. So there was stuff by Newton, and there was stuff from Copernicus, and stuff from Kepler, and different ones. So it's not just his work. A lot of it was based on the law of gravity from Newton, and there are a couple of translations of it. So just to put this into kind of a perspective, it said that Laplace was concise. So what he would say was, I'm looking at this and it appears obvious that such and such and such and such. Or from this information you can clearly see such and such and such and such. Okay. It's not known if he really clearly saw those, like he could connect the dots and see where that was going, or if he was just like, I'm not going to bother with the time on this, or if he just didn't know it. He just assumed things. We don't know. But one of the translators, it was translated to English by an American, and this was years later. What's his name? I don't even have his name. I think it was Nathaniel something. He did 4 of the 5 volumes, and what he said was, anytime I saw where Laplace wrote, it is easy to see, if he saw something like that, he said, anytime I saw that, I knew that I was going to have hours of work ahead of me. This translated to him to hours of work to show the intermediary steps. Because it's not enough just to translate it into English. We want to make sure that the math is easy to follow also, right? So he said, if he said it's easy to see, that this is going to take a while for me to fill in the gaps, basically. So that was one of the translators. The other translator I want to talk about, and one of the reasons I'm going to be honest, is because she's a woman. We don't have a ton of women mathematicians from these days in our history books, so I'm going to talk about her. Mary Fairfax, and her last name is Somerville. Mary Fairfax Somerville. Her dates are 1780 to 1872. Okay, she's actually Scottish, so again, that's an island up where the UK is, right? She's a widow. Her husband was named Grieg. Widow Grieg. Grieg. Not important to her husband's name, what her husband's name was, except for this interesting little story that happens with Laplace. So it said that, and there's confirmation, that Laplace actually did some traveling. In one of his travels, he went to Scotland, and he was having dinner with the Somervilles, and Mary Fairfax was there, and he said he was astounded that she had read his books, I guess, and even more astounded that she understood them, seemingly understood them. And what he said was, you're one of only 2 women who understands my books, And he said, one is you, and one is the widow Grieg. So, he didn't know that Somerville, Mrs. Somerville, was the widow Grieg. And he had been, I guess, communicating back and forth with the widow Grieg. And so in his mind, they're two separate women. And he said, it's interesting that the only two women who read my book and understand it are both Scottish. And it was really just one. Just one woman, dang it. Okay. So she belonged to this, or was persuaded by this society. I don't know if she actually belonged to it or not. It's called the Society for the Diffusion of Useful Knowledge. We had such nice, long, descriptive titles back then. And this society, and Laplace was still alive, this society convinced her to write a transcription, or to transcribe it. Translate. That's the word I'm after. And not just translate, they wanted it to go to English, but they didn't just want it to be translated, they want it to be easy reading for the English reader, basically. So again, she's going to have to fill in gaps. Now, and at this point it was said she was about 50 years old, so she wasn't just a young girl or something like that. And she kind of didn't want to do it. She agreed, the agreement was that she would try her best, and if she didn't do a really great job of it, because she was like self-educated, she didn't have a lot of tutoring or whatever, so she was worried that she wouldn't be up to the task. If she didn't do a good job of it, that they would destroy it and it wouldn't be a big deal. So she writes her translation in her exhibition or whatever, where she exhibits what all the things are. It was published in 1830, which is actually after Laplace's death. And they say that it was so good, such a good book, that it became mandatory reading for anyone studying math and science, well, math and astronomy, which is a science, but not like everybody. Math and astronomy in British universities. And they used it for 100 years. So she was worried that it wouldn't be that good. But it was so good that not only did they publish it, and in fact it said that like the publisher published just a few books, like okay, we'll put out 700 books or 800 books, something like that, and we'll see, and that it is used so much that then they started coming out with different versions of it. She had a foreword in there that was kind of background math material, and they pulled that out and made that into its own little book that kind of talked about these are the background things you need before you even read this thing. So they had different versions and different things that came out, which was kind of cool. Because of this, she was elected into the American Philosophical Society. So she's Scottish. She wrote something in English for British universities, basically. But it got the notice of the American Philosophical Society. And this is 1830, so it's fairly recent-ish, like in the last couple of hundred years, right? She was nominated into it in 1869, which is just a few years before her death.
So before it was published? Nope.
No, it was published in 1830.
Okay.
And then they wrote lots of different versions of it that got used for different purposes. And then she was asked to join in 1869. And this was at the same time as Charles Darwin. So I find that interesting because they thought that her book was significant enough to nominate her into their society, Philosophical Society, at the same time as Charles Darwin. So that's interesting. Pretty good. All right. So that kind of wraps up Laplace. There's tons of other stuff, and we'll actually see him if you look throughout society or throughout history. You see Laplace actually comes back and does different things. Like we see him with as part of Gauss's story, and he's just really he's communal is the word I'll say. Like he's willing to work with other people and talk to other people, and that actually pays off for him. Okay, there we go. That's it for Laplace. Okay, which means that we need to kind of try to wind our way around to Gauss. I want to hit Mersenne real quickly because your book covers him a lot, and then I'll save the last little bit of time in today's class for Gauss. I may even stop and make a new video at that point. So let's talk about Father Mersenne, or Mersenne. Depends on your pronunciations, I guess. I'm terrible at French, so. Okay. He's Jesuit educated. He's a friar for the order of Minims, M-I-N-I-M-S. Sorry, that's terrible. There we go. Which makes me think of like minimalists maybe, minimalists. He is definitely a theologian all the way, and actually if you look in the book, his picture, they have him in like a friar's, what is that called? It's like a cape or something, like friar's robes. That would be it, I'm sure. Okay, so that's even the picture that they use for him. So it's interesting because he actually, his name, you may have heard it before, he has numbers named after him. It's called the Mercen Numbers or the Mersenne primes. Okay, so he has stuff named after him, but it's said that he really didn't offer much in the way of new math. Okay, he didn't do much new math. He was educated enough and smart enough mathematically that he could understand and appreciate other people's math, but he wasn't cranking out new stuff himself. So it becomes a question of, well, why do we care? Well, he actually did a couple of really cool things. So he's the first example that we know of mathematicians gathering just to talk about math in formal meetings, which we would call today a conference. Okay? Kind of leads to conferences. He did this, he would have people, mathematicians, come to his monastery, and this went on for years, from 1635 to 1648 until he died. Okay, people would come to the monastery, and it was all kinds of people. So people who are said to have come to his monastery to talk to him about math include Pascal and Laplace. Okay, so come to him. And why would they bother coming to him when all he does is have these gatherings or whatever? He actually set up a network of communication. And your book calls him a clearinghouse for information. Okay, so that's what he was doing. And this was in France, I think Paris. Yeah, I think he moved to Paris, and that's where he became the clearinghouse for information. So how does that work? Well, they found out after he died he was conversing with no less than 78 different mathematicians. So he would send letters. Let's say he emailed Galileo, and that is one of the people that he wrote with. So, for instance, he would write Galileo, and he would find out whatever new stuff Galileo was working on. And in fact, he did some translations of some of Galileo's early work because it was written in Italian, and a lot of people don't read Italian, so he would translate it into languages that people could read. He would write him, he would get information, get the latest news basically, any new math that was going on, things that were being investigated, so on and so forth. And then what he would do is he would send it out to other people. He's like his own listserv or something. Okay? He would send it out to other people. And he would do that. He would send people new information in exchange for, you need to give me your information. So what are you doing in math? And what are your newest things? And what are your questions? And he was actually really good at asking questions, is what they said. So he might not have known the answer. He might not have known how many of these numbers are going to turn into Mercen numbers, which is what he's known for. But he asked the question, okay? And he got other people thinking about it and working on stuff. So say that Descartes and Pascal came to his monastery and wrote stuff or talked about stuff. If there was something new that was found at the monastery, like new math that they came up with in the monastery, he would ask questions, he would gather information, he would write things up, little papers and stuff, and he would distribute them to all of the people. So it's the early version of an academic journal, if that makes sense. He has this lovely network going on. Okay, so that's what he was good at. Okay, so your book actually says, and it's not that important, but your book says that these meetings at his monastery and the way that he's doing things, acknowledging math and science knowledge and stuff like that that's being developed in the moment, it's a precursor for what becomes the Royal Academies of France, right? So, which is similar to the Royal Society in London. Okay, those are both societies that are honoring people who have great works in their areas. So, yeah, Mersenne is supposed to be the one who led us that direction. So, what do we care about him? There's an area of number theory that talks about perfect numbers. Don't know if you have heard of perfect numbers or not. Pythagoreans actually are the ones who gave these numbers that name. If you'll remember, Pythagoreans thought everything is number and it's really important what the number stands for and this and that. So these things, what it is, you know you have a perfect number if you have a number and all of its divisors added up give you that number, with the exception of the number itself, okay? Or, so there's two different ways to think about it. So n equals the sum of all the divisors of n, except for n. Those are like proper divisors, right? Okay. Or you could say if sigma of n is the sum of all the divisors of n, then that would be 2n. Okay, so for instance, examples help, right? Okay, 6 is a perfect number. If we go n equals 6, the divisors of 6 are 1 and 2 and 3 and 6. Okay? So either we add up all of the divisors except for 6, 1 plus 2 plus 3 is 6, okay, and we get back the number itself, or we sum up all of the divisors, including the number itself, and we get 2 times 6, or 12. Okay. So it just depends on whether or not you want to add the number itself in there. And there's two different definitions, and you can see a lot of them going throughout history. Like some people will be like, no, I'm just looking at these other divisors, not in itself. And some people are like, no, you look at all of them, and then you just realize that it's twice your n. So however you want to think about it. That's a perfect number, okay? And for some reason, people are fascinated with them. There's a lot of work that goes involved in them. Pythagoreans knew about them, and they had several. So they knew that perfect number number 1 was 6. Perfect number 2 was 28. So we'll see that in a second. Perfect number 3 was 496. And perfect number 4 was 8,128. And we're only on the fourth one, and we're getting pretty big, right? So it becomes a matter of, and they're starting to space out between them. It's getting bigger and bigger, the spaces between them. So it becomes a matter of how many of these perfect numbers are there? How can we find them? Okay, so because we probably don't want to be, I mean, I don't know about you guys, but I don't even want to be looking at 8,128 and figuring out all of its divisors and adding them up if I don't have to, right? So it becomes a bit of a thing. How can we make this happen? Euclid actually looked at this stuff. Euclid said this in his Elements. This was his proposition. If the sum is 1 plus 2 plus 2 to the second plus 2 to the third plus ... 2 to the k plus 1. I'm sorry, k minus 1. I don't want to lie to you. 2 to the k minus 1. If that guy is a prime number, we'll call it P. If the sum of all of that equals some prime number P, okay, then we know that P is a perfect number. I'm sorry. 2 to the k minus 1 times P. Let me not lie to you. Is a perfect number. Okay, so let's look at one. Let's do 1 plus 2 plus 4. Okay, 1 plus 2 squared is 4. That's 7. Right? So is that equal to a prime number? That's his if. If you add up these things and it equals a prime number, yeah, 7's prime, okay. Then what they're telling me is this guy right here, it becomes my 2 to the k minus 1, right? That guy times 7, which is my prime number, 4 times 7 is a perfect number. And in fact, 28 is the second of the perfect numbers that the Greeks, the ancient Greeks knew about. So let's look at that. 28 is the same as 1 plus 2 plus 28 is divisible by 4. 28 is divisible by 7. And 28 is divisible by 14, right? So 14 is half of that number, 7, that's 11, 12, 13, 14. Sure enough. Check it out. It works. These are a perfect number. Okay, so this was Euclid's proposition, and he was like, okay, let's see if we can do this. It actually is proven. So, and whenever they proved it, they used Pythagorean work. Okay, so it's kind of cool that they interplayed with one another there. Okay. The next time we hear about these perfect numbers is from a guy you might have heard of. His name is Leonhard, Leonhard. Euler. Sometimes people say that Euler, but it's Euler is the way he said it. 1707 to 1783. So he's right here in this time period where we're looking at these perfect numbers. He said, okay, look here. You have an even number n is perfect if and only if, so he had that if and only if thing going on. N is equal to 2 to the k minus 1 times 2 to the k minus 1. Okay? That was his proposition. That's what he thought. Okay? So he said, using the same thing we already know, let's look at this 2 to the k minus 1, that power of 2 that we're going to add together, right? And multiply it by 2 to the k minus 1. Well, if we look at 28, we had 2 to the second was 4, right? So which of my powers of 2 am I on that I would get 2 to the k minus 1 gives me 7? 2 to the third would be 8, right? So 2 to the third minus 1 gives me the 7. So this works if we're looking at the third power of 2 is what he said. Okay? And he thought that this guy right here is prime. That's what Euler thought. He said 2 to the k minus 1 is a prime number. Okay? He also said there aren't any odd perfect numbers that we know of, period. Okay? And in fact, it was later proven, it hasn't been proven that there are no odd perfect numbers. Okay? But it has been proven that there are no odd perfect numbers less than, and it's crazy to me that people would do this, less than 10 to the 300th power. It has been confirmed that there are no odd perfect numbers less than, oops, I just skipped out on that completely, less than 10 to the 300th. So in other words, somebody has checked all the numbers through 10 to the 300th power. He also, or somebody figured out that there are no known odd perfect numbers with fewer than 8 different prime factors. Okay. So maybe that's 8 different prime factors up to 10 to the 300th. I don't know exactly if those go together. But still, who's looking at individual numbers that have 8 different prime factors to try to see whether or not they fit this perfect number thing? And by the way, they didn't find any that are odd. So now you're looking at it going, okay, well, if we didn't find any, does that mean that there aren't any? No, because there's no proof for there's not. So it's actually an unproven theory that there aren't any odd perfect numbers. But we don't have a conclusive proof, so we can't absolutely say it. So where does Mersenne fit into this? He actually posed the question, and gets people to talking and working mathematically. For what values of k is the integer 2 to the k minus 1 a prime number? Okay. We know a couple of them. We know 7. Okay, that's a prime number. We know 3. 2 squared minus 1, that's 3. That's a prime number. So this actually becomes known as looking at Mersenne numbers, even though he's not the one that came up with that 2 to the k minus 1 guy, right? That was Euler, okay? But these guys, where we're looking at them, these become called Mersenne numbers. And if they happen to be prime, they get called Mersenne primes. Absolutely. Because he's the one asking the questions. So it becomes a huge look for these. At some point, Mersenne puts out on his own, and again, his mathematics was not the best. He could understand and appreciate, but he wasn't good at it. But at some time, he states, okay, there are these Mersenne numbers, m sum n, equal to 2 to the n minus 1, n is greater than or equal to 1. He stated that there are multiple primes in this number, in this set of numbers, basically. And he said the primes are 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 257. Okay, for all the prime numbers less than or equal to 257. So all other numbers in this format, other than these guys right here, all of the rest of them are composite. That's what he said. Okay. And what they said was that some of his contemporaries knew there's no way he's proven this. Okay, there's no way he's looked at all of these numbers. He's just kind of guessing. Maybe he's proven some of them aren't, like maybe he's figured out that 11 isn't one of these prime numbers, but he doesn't know for sure which ones are or which ones aren't for these things, because M127, the Mersenne number 127, has 39 digits. Okay. M257, that's the other one that's a huge number there that he claims. That guy has 78 digits. That's how long that number is whenever you stick in 257 and figure out that Mersenne number. It's huge. And he did not go through and figure out what all the factors of it are any of the other primes numbers less than that going to go through it. So, yeah, we know it's not true. We actually do have some other prime numbers, though, that start, or some other perfect numbers that are found through this demonstration, through this exploration, I guess you would say. There are some other prime numbers that are perfect numbers that get found. So the Greeks knew 6, 28, 496, and 8128. But Euler came up with a couple, and a couple of other people really contributed. One guy that was contributing was still working with Roman numerals. Your book points that out. That's funny to me. The next number, P5, perfect number 5, is the number 33,550,336. I can't imagine somebody looking at this number, perfect number 5, and going through all of its factors and then adding all those up to make sure it still equals 33,550,336. So it's interesting because Euler's the one that came up with this guy, and it's the first advance, so to speak, in perfect numbers since the ancient Greeks. Okay, because the ancient Greeks had those first 4, so it's the first time we see, oh, there really are others out there, and we can find them. It just takes a while. Perfect number 6 is 8. What would this be? Billion? 589,869,869. and 56. Oh my gosh, who does this? I don't know. It's not me. I'm spending my time on other things other than finding perfect numbers like that. But you can see, again, we've got this progressively growing thing. It's really getting big fast. And we see that the gaps in between the numbers are really getting big, exponentially so. They're really growing quickly. They've got some other numbers where they just start, I'll show you one of them, for instance, P9. It's easier to talk about it in terms of its format as using Mersenne numbers, so that's why Mersenne comes in. 2 to the 30th, that's the power of 2, times 2 to the 31st minus 1, that is the Mersenne number right there, right? 2 to the k minus 1, where we're using 31 as the prime. So this number, and I'm going to give it to you, it's crazy. You don't even have to write it down. It's 2, 305, 843, 003, 139, 952, 128. Okay. So this is how we know Mersenne did not actually work with these numbers, because they're huge.
31, is it, I didn't write it down, but does it have to be prime?
These numbers here are supposed to be prime in order to be Mersenne numbers. So you're using, and in particular, they're using odd primes, so not 2. So 2 to the prime number minus 1, Mersenne numbers. And this is one of the ones that he had picked out. He picked out 2, 3, 5, 7, 13, 17, 19, and 31. So he said it would work. And it's kind of a crazy number. Perfect number. All right. Lots of study comes up from that. So it's just one of those things. This guy gets his name in the history books basically for posing a question. It's fun. Yeah. All right. Moving on. Gauss, the piece de resistance. He's my favorite mathematician. That's probably a warning for the next exam. I like Gauss a lot. He's the one I wrote my master's thesis on. So, my research paper. His dates are 1777 to 1855. We've actually talked about him in here. There's some stuff about him I didn't mention before when we were looking at Gauss's formula. There's lots of stuff. He was known as an infant prodigy, okay? And according to him, he says that he could reason and he was making logical conjectures before he could talk. I don't know how much we're doing at the age of 2 and 3, but apparently he was a prodigy, so he's different. Okay, so he's a genius, and people use that word a lot with him. At the age of 3, supposedly, he corrected an error in his dad's books. His payroll accounts. Okay, so apparently he was hanging out. His dad was kind of a manual laborer. They were a poor family. His dad did things like canal digging and stone cutting and gardening for people, and pretty much any kind of labor he could have. But he did have people who worked for him, so he did fairly well. And so he paid people, and he had a payroll, and he was working it out, and apparently Carl climbed up on the desk and like marked it out and went, "This is wrong," and fixed it. So at 3, and it's supposedly substantiated by other sources, so believe what you will. At 9, his teacher said they could no longer teach him anything. They didn't have anything new for him. And it's actually interesting that he even went to school, because with his father being, with his family being poor and his father being a laborer, he actually thought that, Carl should just basically apprentice with him and figure out like the family trade and be able to, garden or cut cut stones or something like that, be a mason. And so he's considered the prince of mathematics. Your book and other places call him the greatest mathematician of modern math. Modern being from the 1700s, but still. And he almost was a gardener, basically. So I don't think he would have done very well doing manual labor. We know that by 10 he had developed, let's say found, how to add consecutive numbers, the story that we have about his teacher putting him to work adding 1 through 100. We've already talked about that earlier in the class, so I'm not going to berate it or beat it in. It is said, and your book doesn't go into this, I don't know why, it is said that he had his formula by the age of 15, and that by the age of 17 he had proven it. So I don't know why your book doesn't talk about that, but that's pretty young to be coming up with a mathematical formula for something like this and giving the proof for it. But again, supposedly a genius here. So at some point he catches the attention of a duke. Duke Ferdinand of Brunswick. So I don't think I mentioned that we're in Germany here, right? Gauss was German. In fact, if you read different books about Gauss, it says that he was so German that never once in his entire life did he leave Germany. Germany is pretty small. We're talking for sure less than the space of Texas, right? So he was so German that he never even left Germany in all of his life, and he didn't want to. He was offered to go places, to travel, to talk to different people about mathematics and that kind of thing, and he always turned it down. He was offered positions not in Germany. He would not go. So he did not want to leave Germany, is what we take from that. At one point he let's finish this out. So Duke Ferdinand of Brunswick, he becomes his patron, okay, which means that he supports him, right, and sends him places. He sends him first to basically a preparatory school, and then later he sends him to the University of Göttingen. G-O with the umlaut on it, T-T-E-N-G-E-N. University of Göttingen. He was only there for 3 years, 1795 to 1798. He's supposed to be working with a couple of mathematicians, a couple of teachers, and one guy in particular just wasn't interested in anything that Gauss was doing, and that was supposed to be like his primary lead mathematician. So it said that Gauss just worked on everything independently, just basically didn't even go to classes because he wasn't learning anything there, so he's just doing stuff and learning stuff on his own. So he actually, while he's here, he puts together the method of least squares. Okay, which is a way of looking at data points and figuring out basically a trend line, right? So method of least squares. He actually shares that honor, so to speak, with Legendre. It was said that at the same time they independently came up with that, but a lot of times Gauss gets a bit of the credit there because he's such a young genius. And at 19 he did the thing that really won him a lot of notoriety, and it was said that he wasn't sure which way he was going to go in his career. Like, am I going to look at math? Am I going to look at astronomy? Is something else more interesting? But at 19, he determined that you can construct a 17 gon. Okay, and by construct we do mean construct using only a straight edge and a compass, the way the ancient Greeks did, Euclidean methods. So he used only a straight edge and compass and constructed a regular, I should throw in that word, regular 17-sided polygon. Okay, so think about that. The ancient Greeks didn't have this at all. This is totally new math that he's come up with, and for who knows what reason, all of a sudden he just turns his attention to constructing regular polygons, which the Greeks could do like triangles and quadrilaterals, hexagons, but nobody had gone this high. I think they could do dodecagons, which is 12-sided, but they could not do 17-sided for sure. And this is actually what I did my master's research paper on, and my thesis advisor made me construct it myself from hand with the thing. It was crazy. I have the picture still today. So it's a really, really, really in-depth process where he has to, not estimate, he has to actually show using compass and straight edge things like the square root of, I don't remember, say 1 plus the square root of 5 divided by something, something, and he has to exactly give that using the construction. So what he does is he does the algebra on one side to show this is the math that I'm doing, and then he does the constructions and bisections and stuff like that to show this is really where I divided by 2. This is really where I took the root. This is really where I did that. And so he lines that up together by the age of 19. Does something that nobody's been able to do. And actually it said that whenever he shows this to his advisor's like, yeah. And he's like, but I had to solve a 17th degree algebraic equation to do this. Yeah. He's just not interested. And probably because it was probably above his advisor's head, so he just didn't care. Gauss liked this so much that he requested the 17 gon be put on his, engraved, I guess is the word, on his tombstone. So he wanted to basically copy Archimedes, right? Because Archimedes wanted the sphere inside of the cylinder on his tombstone. And nobody did it. They did not do that at all. However, what happened was years later, there was a monument that was constructed for Gauss. It's in Brunswick, which is like his hometown. It's where the Duke that was his patron was from. Okay, there's a monument in Brunswick, and on it there's a 17-sided star. Okay, which is not what he did. The saying goes that the stonemason who was going to do his monument said that it didn't make any sense for him to do a 17 gon because by the time you got 17 sides in there, it's going to basically look like a circle. And it kind of does, by the way. Whenever you finish constructing the 17 gon, it looks very circular. So the stonemason was worried that it wouldn't come out nicely. So instead they did a 17-sided star. My thought was, well, once you have the star in there, you could have connected those, right? And then people would know it's not a circle. But they didn't ask me, dang it. But yeah, so instead there's a 17-sided star there. Okay. But that's what he thought was his very, like at that point in his life, his pinnacle, so to speak, the most important thing he'd done. I'm running out of time. Nope, I'm good. Oh, I might get it in one recording. That'd be awesome. Okay, so what then? In 1801, he proved that, he proved that any n-gon can be constructed if you have an odd prime. P is an odd prime. where it follows this formula. 2 to the k plus 1. Okay? So think about that for a second. 2 to the k plus 1. So the exponent in my prime up here has to be a power of 2, right? So for instance, for 17, it would be 16 plus 1, right? So it's how can I put this together? Where this gives me, we know 16 is 2 to the 4th, right? Okay. So then I'm actively looking out there, looking and searching for these k's, right? Where I can figure out what's the power of 2. So what if I'm looking at this would be 2 to the 2nd power. What if I had 2 to the 3rd power? Well, that would be 2 to the 3rd power is 8. So now I've got 2 to the 8th, and I want it plus 1. So does that give me a prime number? So that's what he was looking for. And the numbers that he came up with where this actually works, where you do get a prime number, are 3, 5, 17, 257, and 65,537. So these are the ones that he knew. If I use this format right here, I get a prime number. Okay. So not always do you get a prime number, right? But sometimes you get a prime number. And when you do, then he proved that you'll be able to construct an n-gon with that many sides. I don't think anybody ever tried to construct the 257th gon, okay, but he mathematically proved it. So we don't have to construct it anymore. We have a generic proof, right? Yay. Okay, so he's here, he does this, all of this kind of stuff. Whenever he finishes up at university, he's tired of it. He actually goes back to Brunswick. And he's going to tutor people. That's how he's going to make his living. Unfortunately, there aren't a lot of, Brunswick's not that populated of a place, and there aren't a lot of people who want a mathematician tutor that can give them all this high-level research stuff. So he's not making much of a living, and so actually Ferdinand comes back and supports him again because he says, I don't want you to be worried about financial needs. I want you to be free to do this math that is so important. So Ferdinand supports him again until he dies. He was killed abruptly in a battle. And it said that Gauss was very distraught because he's going to have to make a living and he can't do it in Germany. So he's getting offers for places outside of Germany. He doesn't want to go outside of Germany. So it said that his friends got together and found him a job. That's just sad. It's at actually the University of Göttingen, which is where he went to school, so he's familiar with it. And it's as the director of the new observatory there. And there's a story or a little thing that goes that once he became the director of the observatory, he stayed there in that job for about 50 years. He never left that job because it was something he was either good at or they didn't care if he was good at it or not because he was there doing math and science. And once he got in there, it said that except for he went to one little conference one time in Germany, but except for that one trip, he never spent a night not in his own observatory. That's what they said. He always stayed there. So he's kind of a homebody. Okay. What else? His doctoral thesis was on the fundamental theorem of algebra. Which there were already, let's say, people who knew about the fundamental theorem of algebra, But he first of all gave it the name, Fundamental Theorem of Algebra, so he named it, so yay. And then second of all, he gave a proof. It wasn't as nice of a proof as we might have had today, but because he was able to put a proof on it, that he kind of gets credit for, I don't want to say discovering the fundamental theorem of algebra, but for sure for fostering it a little bit. So you guys know what the fundamental theorem of algebra is. It says if you have a polygon, well, there's a precursor for it. So say I have y equals x to the third. It can be however crazy of a polygon it is. We all know how many solutions does that thing have? 3, right? Okay. And so they already knew there were 3 solutions, or that's what they suspected. But what he came up with is that there is at least one complex solution. And so they know about complex. Euler actually is the one who pushed us towards complex numbers. We kind of skipped him a little bit, but I wanted to do Gauss. So anyway, you can look at Euler. He actually comes up with complex numbers have conjugates as solutions. We know that. So if 3i is a solution, then we know that negative 3i is a solution for one of these algebraic equations, right? So Gauss is the one who comes up and says, okay, not only is there a solution, but it's either real or complex. And then we start seeing this thing, and the way you would use it in algebra today would be that if I have something like x to the third, even if I have 2 complex numbers, right, solutions, because I need conjugate pairs, even if I have that, there's going to be one that's a real solution, right? So it's going to somehow cross over the real axis, the x-axis on the coordinate systems. So we know that we have one solution. And in modern algebra, it even goes so far as to say, if you know that your y value is negative here, and your y value is positive there, then you know that somewhere in the middle of there is a solution, a real solution, and that it had to have crossed over right here, because if it's a polynomial, then we know that it's continuous and smooth, right? It's not going to jump here. So yeah, we know that there's a real solution in there. So he's the one who was pushing that forward, and he was able to write a doctoral thesis on it and get some recognition. Okay. One last thing, well, 2, I'm sorry. He wrote a book, Disquisitiones Arithmeticae, something like that, which is basically arithmetic, that is terrible. Arithmetique. Oh my goodness. Arithmeticae. I left off a syllable. Sorry, guys. Arithmetique, I guess. I don't know. Which is basically saying that he's writing a disquisition is like expedition, so that kind of thing. He's writing an expose on arithmetic, basically, is what this boils down to. And it's all about number theory. So you may have seen some of his work on modulos. Okay, he did a lot of stuff about modulus stuff. Okay, so that's his book that he wrote. And then his thing that got him worldwide acknowledgement, I would say, is his theoretical astronomy. Okay, and I'm going to stop this and start a new recording because it's about to cut me off. Dang it. So close.